Okay, we've learned in quantum theory that orbitals are the 3D regions in space around nuclei where we expect the electrons to be found. So now we're going to draw pictorial representations of those electrons in those orbitals. You'll see that this diagram I have up front here is called an energy level diagram. So there's an arrow on the left indicating an increase in energy. Capital E stands for energy. And you'll recognize the sub-level designations here, the 1s sublevel, the 2s sublevel, the 2p sublevel, 3s, 3p, 4s, 3d, 4p, 5s, and so on. I just went as high as 5s here. Now, the order of how I've shown these increasing will be addressed later, but just notice that because the arrow is increasing in energy upwards, that the 1s sublevel is the lowest energy sublevel, then the 2s, then the 2p, and so on. By the way, these gaps are not to scale. There is the greatest difference in energy between the 1s and 2s, and as you move up, the sublevels do get closer and closer in energy. However, that becomes very difficult to print clearly, and so it's written like this. All right, so what about the number of lines or dashes that I have in each sublevel? Does that make sense to you? Each line here represents an orbital in the sublevel. So think back to an S sublevel. Does it have just one orbital? Well, for an S sublevel, L equals 0. What's the magnetic quantum number when L equals 0? Also 0. And because there's just one possible value for the magnetic quantum number, there's just one orbital in the sublevel. When you have a P sublevel, L equals 1, and now ML can be -1, 0, and 1, -1, 0, and 1. So here we go, we have 3 orbitals in a 2p sublevel, as well as any p sublevel. When you get to a d sublevel, L equals 2, and the magnetic quantum number, -2, -1, 0, 1, 2, generates 5 orbitals in a d sublevel. And similarly for an F sublevel, you would have 7 orbitals. Okay, so that's a brief explanation of this schematic here. Now there's a few rules we're going to follow. The German word Aufbau means filling up, and so we're going to make sure that we fill up these orbitals by having electrons occupy the lowest energy orbital available. So the 1s would be the lowest energy orbital, and that's where we'll put our first electron. And once it's full here, then we have to move up to the 2s, then the 2p, and so on. Hund's rule is going to relate to when we have multiple electrons in a sublevel. So we're going to make sure to half fill each orbital in the sublevel before we pair them up. And Pauli, you've already seen the idea that there needs to be a unique set of 4 quantum numbers for each electron. So we'll see what implications that has as we start these diagrams. All right, so I'm going to use green, I guess, here, and I'm going to use arrows to indicate electrons. So hydrogen has 1 electron, so I will follow Aufbau and place that 1 electron as an arrow in the lowest energy orbital available, which would be the orbital found in the 1s sublevel, the 1s orbital. Okay, so I've placed that electron. I didn't put a complete arrowhead. You could, but now that I'm going to move on to helium and put 2 electrons there, I'm going to put a second electron into this orbital. Now, I better make sure that I'm following the Pauli exclusion principle. So, take a quick moment and remind yourself of the values of the quantum numbers for this electron. Okay, and so we see n equals 1 because of the 1 here in the sublevel designation, L equals 0 because that corresponds to an S sublevel. When L equals 0, the magnetic quantum number runs from -0 to +0, -L to +L, which is really just 0 in this case. And because I'm pointing the arrowhead up, I'm referring to the positive spin. So now, according to Pauli, the next electron, like no electron can have the exact same set of 4 quantum numbers. So if I'm going to do the second electron of helium, then I'll put that in spin down. And hopefully that makes sense to you because the 1, 0, and 0 are still going to be the same for this second electron, but now the spin will be -1/2. So if you were asked to do an energy level diagram for helium, you would need 2 electrons, and that's where they would go. By the way, you don't need to draw all the sublevels and orbitals that are not being used in a particular diagram. I just wanted to set it up so we could add quite a few electrons. Okay, if we're moving on to lithium, there would be 3 electrons in total. And so the first 2 would go in the 1s orbital that we see, and then the third electron, following off bow, would go into the next lowest energy orbital available, which is the 2s. And so on. Now, before I get too far ahead, I would like to introduce the notation of electron configuration. You can imagine that this drawing a lot of electrons into an energy level diagram would take a fair bit of your paper, right? And so it would be rather nice to have another way to represent the electron distribution. So for hydrogen, we just had the first green arrow, right? Where was that electron found? In the 1s sublevel, right? And there was 1 electron there. For helium, we had 2 electrons, right? And they were both found in the orbital in the 1s sublevel. There were 2 of them. Now don't read this as 1s squared, and I know in math that would be, very, very correct. But in chemistry, we read it as 1s2 because in fact that exponent is indicating the number of electrons in that sublevel. When we move on to lithium, which is the diagram we have up there right now, 1s2, 2s1. So you go ahead and do beryllium. So place the 4th electron. Where does it go? Follow off bow into the lowest energy orbital available. There we go. And now we can indicate the electron configuration of beryllium. 1s2, 2s2. Okay, let's keep going. Energy level diagram. Boron is next, right? So we have another electron. Where does it go? Well, the next lowest energy orbital available, right? And we look and we see the 2p sublevel is the next one. So I'll put, by convention, we put it into that first orbital of the 3. And so there we go, having boron, 1s2, 2s2, 2p1. All right, now what's going to happen with carbon? Carbon has 6 electrons, 1 more than boron. So I need to go and put that 6th electron in. Now if I put it here, I just broke a rule. Which rule did I break? Reread the 3 on the side. I just broke Hund's. I need to half fill, so I need to put that 6th electron into the second orbital of that sublevel before, right? And they all need to be half filled before I'm allowed to pair up electrons, so follow Hund's rule. The electron configuration of carbon then, 1s2, 2s2, 2p2. Okay, moving on to nitrogen. 1 more electron, where does it go? Follow Hund's rule. By convention, we'll move into that last 3rd orbital and half fill it for a configuration of 1s2, 2s2, 2p3. Okay, keep going. So oxygen, fluorine, and neon. Here we go with oxygen, 1s2, 2s2, 2p4. There's fluorine, 1s2, 2s2, 2p5. And lastly, neon. Okay, so now take a moment, keep going, and do energy level diagrams, like keep filling it in, and do configurations all the way to argon. So from sodium, atomic number 11, to argon. Then check your work. Okay, so you can check your configurations by pausing the video. And I will go back to the energy level diagram here and fill it in so you can watch how I would have created these. So we were at 10 electrons, so 11 for sodium, 12 for magnesium. There would be aluminum, right? Silicon, I follow Hund's rule. Phosphorus, sulfur, chlorine, argon. Okay, just a comment about why I didn't put a third electron. Remember that was the Pauli exclusion principle. So we'll just put this in our notes here, right? That there's max 2 electrons per orbital. Okay, so could you please do potassium and calcium? And after that, I'm going to show you a shortcut. Okay, so here is potassium and calcium's electron configurations. Now, are you getting comfortable with this order of sublevels? It's pretty repetitive, isn't it? Wouldn't it be great if there was a shortcut? I mean, the electron configuration is definitely easier to do than drawing out the whole energy level diagram, but notice that argon has 18 electrons, right? Atomic number 18. And these 18 electrons are configured in these sublevels as shown. Well, aren't the first 18 electrons of potassium identical, right, in their placement? They certainly are. We follow Aufbau and we fill the sublevels. Calcium, same idea. So the shorthand electron configuration actually involves putting the previous noble gas in square brackets, which allows us to then represent those 18 electrons abbreviated, and then we just add on the remaining electrons. So for potassium, the 4s1 electron. For calcium, argon, and then 4s2. Now you could do a short form for, let's say sulfur. Go back here to the sulfur one. Now go to the previous noble gas. So the previous noble gas before sulfur, if you look at a periodic table, right, is neon. So there's the electron configuration for neon. So for sulfur, we could have put neon in short brackets, in square brackets, and then added on the 3s2, 3p4. I needed you to write out a few of them, so that you would start to get the hang of how it works. Don't use the short form until you understand the detail behind it. Okay, so just backing up now to our energy level diagram, I can bring, there would be potassium, right? And then there would be calcium in the energy level diagram, all 20 electrons. Okay, so where's the next electron going? The 3D sublevel. So it's going to go into the first electron of the 3D sublevel. So notice that argon, right, would be all of these electrons here. There's the 18. So we'll have argon in square brackets and then 4s2 3d1. And that'll be for scandium. Okay, now do titanium and go all the way to zinc. All right, so from titanium number 22 to zinc atomic number 30, and use the shorthand. Okay, so there we go. You can check your answers. And I'll move back up to the energy level diagram here and keep going, right? There's 3d2, 3d3, 4, 5, 6, 7, 8, 9, 3d10. And there we have zinc. Okay, so how are you going to know the order of this filling here, the order of these sublevels? Well, let's make the connection between quantum theory and Mendeleev's periodic table, which incidentally, the shape of which was created prior to the quantum theory being developed. Okay, so take a look now through all these configurations for the elements found in group 1. So hydrogen, here it is here, 1s1. Lithium, 1s2, 2s1. Sodium, 1s2, 2s2, 2p6, 3s1. Potassium, argon, 4s1. So study those 4 configurations and see if you can find something common about all of those configurations of all elements there in group 1. Okay, hopefully you've noticed that they all have an S1 ending. All right, go ahead and find the configurations for beryllium, magnesium, and calcium. What do you notice about the beryllium, magnesium, and calcium configurations? What do they have in common? Okay, hopefully you've seen that they have S2 endings. S2, S2, S2. Check out boron and aluminum. P1, P1. Carbon and silicon. P2, P2. Nitrogen and phosphorus. P3, P3. And so on. P4 for oxygen and sulfur. P5 in group 17. And P6 for neon and argon. Now, it's true that helium's over there in group 18, and it does not have the P6, but it doesn't even have 6 electrons, right? So it's a bit of an exception over there. And yet, when we look at the energy level diagrams, we remember, oh yeah, so helium had 2 electrons in that 1s orbital, and that filled that sublevel, didn't it? And when you look at neon and argon, they finish with P6s, so they're filling those sublevels also. And so helium is placed over in the noble gases because of its full and very stable configuration. Okay, so now let's look at what you did for scandium and etc. Notice the endings here, D1, D2, D3, all the way to zinc, D10. Right? So there are 10 rows, 10 groups in the transition metals, right? And 10 electrons in the D sublevel. And as we eventually fill up that D sublevel, right, we finish with zinc's configuration. All right, so look at the periodic table and see if you can notice now the placements of these elements and their location in the table. There are definitely some patterns here that we can notice. So this is a pictorial representation of what we've just been discovering. You'll notice these are the endings of the configurations. So notice the S1, S2, P1, P2, and so on. Okay, so this schematic actually shows the entire periodic table and all of these sublevels, and where they end. So this is from page 168 in your textbook. So if you wanted to check that out, you certainly could. Now, because you're always going to have a periodic table as reference, what you need to learn are these blocks. And notice here that groups 1 and 2 are definitely the S block, right? Having the S1 and S2 columns. And over here, groups 13 to 18 are the P block. Groups 3 to 12, are the D block. Okay, and then the lanthanides and actinides down here are the F block. All right, so having a periodic table in front of you, if you had to do the electron configuration of, let's say, gallium, which would be right here, that's the one after zinc. Okay, so if you need to do the electron configuration for gallium, you would start up here with the first electron, that would have been hydrogen, right? And we'd think 1s, right? And we'd put 1 electron in there, but then we would need to fill it, so 1s2, because we have to get all the way up to 31 electrons for gallium. So 1s2, 2s2. Just keep reading left to right following atomic number. 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. If you want to do the shorthand, from this element back up to the previous noble gas, which would be argon, and then argon in square brackets, 4s2, 3d10, 4p1. If you had to do thallium, way down here, 81 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, jump down here, 4f14, come back up, 5d10, 6p1 for thallium. So when you get to the 7s here, you just have to drop down to the 5f before coming back up to the 6d. What do you think this sublevel would be here? This schematic is a bit older, right? We do have elements going all the way across here. So this was 6p here. This is the 7p sublevel. Yep, 7p. 1, 2, 3, 4, 5, 6. Okay, I just want to comment on the number, the value of n in the sublevel. Notice in the S block, 1, 2, 3, 4, 5, 6, 7 matches the period number. Same thing in the P block, 2, 3, 4, 5, 6, and 7p if it was there. So the S and P block match the period number. The D block, if you're in the 4th period, you have to subtract 1. It's the 3D sublevel. If you're in the 5th period, it's the 4D sublevel. And notice for the F block that you have to subtract 2 from the period number. So period 6, 6 minus 4, it's 6 minus 2, it's the 4F. In period 7, 7 minus 2 is 5, and so it's the 5F sublevel. So basically, when you look at a regular periodic table, you need to be able to count out, right, write out the order of these sublevels and write your electron configurations. Okay, the last part of the lesson is looking at 3 concepts, 3 extensions from the basic knowledge you just learned. So first, ions. What if we need to write a configuration for an anion, a negative ion? Well, you fill up the sublevel. So we know atoms gain electrons to become stable and form negative ions. Well, here's the chlorine atom, shorthand electron configuration of neon 3s2 3p5. So you notice that 3p5 is not full, so let's go and fill it up, right? So that becomes a 6. All right, and so we have 1 electron gained, and so that's the -1 charge on the chloride ion. Now, should we be writing all of this like that? Well, no, we've actually got 18 electrons now, isoelectronic with argon, same number of electrons as argon, and so we replace all of that with the square brackets and argon. So the shorthand configuration, electron configuration of the chloride ion is argon in square brackets. Okay, for cations, we remove electrons from the sublevel with the highest value of n. So let's look at sodium here. The values of n for these sublevels, 1, 2, 2, 3. So the one with the highest, which sublevel has the highest value of n? That would be the 3s. So we remove electrons, we look to empty that sublevel. So if we're going to remove this 1 electron here, then we'll be left with 1s2, 2s2, 2p6. And we can see that filled 2p sublevel now, right? Together with the 2s2 is a full valence shell. Now, could this be replaced with the shorthand of neon? Certainly it could be. Okay, try zinc. Remove electrons from the sublevel with the highest value of n. So hopefully you're choosing the 4 here. So we're not just going to eliminate one of those electrons, right? We'll remove both, because in doing so, we completely empty that sublevel. And this corresponds to something you learned in grade 11, that zinc is not multivalent, that it forms +2 ions, and we can see how removing those 2 electrons leads to a very stable particle, full D sublevel. Okay, next I need you to be aware of a couple of exceptions, just so that you understand the full potential of this theory here. Transition metal chemistry has not been really explained by any earlier model than quantum, and we can use the quantum theory to help explain the metal ion formation of the transition metals. First, let's look at the chromium atom. So we've done the electron configuration following the rules before, argon 4s2 3d4. Experimental evidence doesn't actually support that configuration. So what the experimental evidence supports is that this electron here actually gets promoted to then half-fill the 3D sublevel. And so this 4s1 3d5 ending is actually the experimentally supported configuration of a chromium atom. And so we see, and the theory evolves to suggest that this half-filled D sublevel also provides for stability in the particle. Something else happens here with copper. We're expecting, according to the rules, a 4s2 3d9 ending, but in fact, experimental evidence supports that this electron is actually promoted to the 3D sublevel, and that we have a 4s1 3d10 configuration. So here the theory evolves then to say that this full D sublevel, right, is lending stability, and that's why we're seeing that configuration experimentally. Here we have a half-filled D sublevel. So I'm not expecting you to go through the table and know all of these exceptions, but I just wanted you to be aware of these exceptions and at an introductory level, so that as you explore in later courses or readings, that you'll have some idea of what's going on there.